Okay, welcome everybody. So we are very glad to have Vahab Mirrokni as our guest speaker today for the RMP webinar series. So let me tell you a little bit about Vahab. So Vahab is a distinguished scientist heading the New York and Zurich Algorithm Research Group at Google Research. So the group consists of three main sub-teams: market algorithm, large-scale graph mining, and large-scale optimization. He received his PhD from MIT in 2005 and his BS from Sharif University of Technology. He joined Google Research in 2008 and spending a couple of years at Microsoft, MIT, and Amazon. So he's winner of several paper awards at very prestigious conference, and his research areas include algorithm, distributed and stochastic optimization, and computational economics. So Vahab, it's our pleasure to have you. So before Vahab gets started, so let me tell you to the audience about how we're going to organize the Q&A. So if you have any questions, I'm going to ask you to use the Q&A feature in Zoom. We're going to collect these questions, and then at different points during this talk, we're going to ask these questions to the speaker. So I ask you to use the Q&A feature. So I think that's it. Thank you, Vahab. It's all yours.
Thanks, Santiago. Thanks a lot for having me here. I'm going to talk about recent trends in online advertising research, and with a focus on robustness, automation, and learning. And I should say that this is what I'm presenting is joint work with many colleagues at Google, at different organizations, Columbia University, MIT in particular. And disclaimer is that what I'm presenting here the focus is on academic research and not Google Ads products. But with that comment, let's start. And now, okay. So first, before diving into the technical topics, let me give you an intro on the online advertising market. The market is still growing. It's a big market, and there are many different types of ad products that show up. At Google, for example, we have Google Ad Manager for display advertising, search ads, shopping ads, YouTube ads, and so on and so forth. Each of these areas have their own research challenges, but they all share similar, basically, problems, and they all also share like similar advertisers who interact through these systems and may spend their budget throughout all of these advertising systems. So what I'm going to cover is actually related to most of these ad products in some sense. Let me give you like a couple of examples of advertising ecosystems. Let's start by display advertising ecosystem. In this ecosystem, there are four major types of players. There are advertisers and agencies that want to show their ads. There are publishers who are basically who provide content, and they show these ads to fund their like content. And then there are ad servers who help basically advertisers connect with publishers and show their ads through maybe reservation contracts, and advertising exchanges or ad networks that run real-time auctions. So there are like interactions between each of these types of entities. And this is in addition to users who are basically watching these ads, and they have to be satisfied for sure. In this type of market, when a user goes to a website, the website sends a request to an ad server. The ad server can decide to show a reservation contract or send the request also to an advertising exchange. The advertising exchange may run a real-time auction between a number of ad networks, and they bid real-time. The ad exchange chooses like a winner, returns an ad to the ad server, and the ad server finally send maybe a set of ads to the publisher to show. And the whole thing should happen in like a matter of tens of milliseconds. So the system and the algorithms and the auctions that are used here should be very simple and very should be implemented in a distributed manner and at scale. Another important example in this market is the sponsored search auction, sponsored search advertising ecosystem, in which we have users, advertisers, and the search platform. in most cases, not only in sparse and search, but like in general in advertising, we sell, the platforms sell clicks or conversions, and they have to also compute click-through rates and conversion rates. So this is the probability that when a user sees an ad, may click on it, or the probability for a user to click and like maybe buy a product or like download a software or something that we call conversion. In this context, the common type of auction that's used is called generalized second price auction. And the idea is to sort bids, sort ads based on their bid multiplied by the PCTR or the conversion rates. And after choosing the top K bidders, the payment is the minimum bid to keep their position the same in this ranking. So this is called the generalized second price auction. The market in general is moving toward automation, and there are a number of popular bidding strategies or automated bidders that are like increasing in volume. The two major types are target CPA and target ROAS type of buyers. The target CPA buyers declare a target cost per action. So they declare a number that we call the target CPA, and they are willing to pay up to their budget, basically pay the platform up to their budget under the condition that on average per action they pay at most this target that they declare ahead of time. In the target ROAS like type of bidding, in addition to declaring this target, they also declare a value per that they have for each type of conversion, and the target is considered to be a target of return over the ad spend. So on average, they want to have the total value over the ad spend to be bounded by something. In both cases, they are declaring an average type constraint to the bidder. So why do we have these automated bidders? The major reason for this is that different type of advertisers, brand advertisers, or basically remarketing, retargeting type advertisers may have different objectives in mind. They may want to maximize clicks or conversions or something else, subject to different type of constraints. But in all cases, they have to translate their objective to a bid to be able to participate in an auction with other advertisers. So these auto bidding systems bridge the gap between the advertisers' high-level goals or objectives and the per query bids that they have to declare. And they simplify this important part of the business. So there are many research questions that shows up as the market is moving more and more toward automation. The major questions are what is, like from bidders' perspective, what is the best bidding strategy? How can they optimize their bidding like algorithms? From the auctioneer's perspective, there is a question of like as we move more and more to an auto bidding board, what type of auctions are more suitable that serves everyone better, like it results in a better market and better welfare in the outcome. And in all of these matters, an important aspect of designing these ad systems is to design robust algorithms and robust auctions in a way that we can like automate easily. We can basically be robust against strategic behaviors, adversarial corruption, like noise in the predictions, like and mistakes, and so on and so forth. So this is actually the major the topic of my talk as well. And for this reason, I divided the talk into 4 major parts. The first part is going to discuss like the auction automation topic and basically the research questions in this area. The second part and the other parts discuss basically robustness against different type of mistakes in the system, against noise, against gaming strategies, and so on and so forth. I guess we'll have some like conclusion in each part, and we will move to the next part. And actually, I also arranged the talk in a way that maybe toward the end it becomes more technical and maybe academic as well. But let's start. So the first part is about auctions and bidding automation board. And I'm going to discuss 4 or 5 papers in this topic. This is actually the most recent topic, and many of the papers here are for like 21, like very recent or working papers. So in order to discuss markets in automation board, we have to understand buyers' objectives, and we have to distinguish 2 utility models for advertisers or for buyers here. There is the traditional economics model that we call utility maximizers. These are like advertisers or like buyers who want to maximize the quasi-linear utility function. They have a value from getting the impression, the object, and they have to pay something. So the quasi-linear, the value minus bid is their utility. On the other hand, the value maximizers under the target constraint have the target constraint as a major constraint that they have to satisfy, but at the same time, they want to maximize their value. So note that in the world that advertisers may have only a budget constraint, this value maximization doesn't make sense as much. So in the context of target-based advertising, that the advertiser or the buyer has basically an average type constraint, that the value minus the target return of investment times the payment should be greater than 0. With this constraint, it makes sense for the advertiser to basically only think about maximizing their value, which could be the number of clicks or the number of conversions or the value of the conversions that they gather. So now, by like after having this in mind, we can actually think about, in particular, value maximizers under target constraint. So having this in mind, there is a question of like what type of auctions are good for this type of markets. The question is, do the existing market auctions, for example, first price, second price, or GSP, appropriate? Can we characterize the optimal mechanisms in this new world? And the answer to first question is maybe. We know that truthful auctions, when you basically simply run a second price auction on bid times PCTR, like in equilibrium after buyer response, they achieve 1/2 of the optimum welfare. So when you run a simple second price auction, you may actually lose in the value of the allocation after you consider the response of buyers. And this is reported in a recent paper by my colleagues at Google in a Wine 2019 paper. So the first thing that we will discuss is how to change the auction to increase the value after the response. Like how can we increase the welfare and efficiency of the market? And then we discuss the landscape of designing these optimal auctions. To understand basically the auctions in auto bidding world, we can, especially in the target-based world with value maximization, we can basically rewrite the ROI constraint and normalize the objective, both the objective and the constraint, like what we see here. So if we do it like this, we observe that if all target ROI constraints are met, the welfare, which is basically the value of the solution, becomes the same as the revenue that we collect, because this, like we will get payment here equal to the value that we gather. So in the case of value maximization, we can say that if targets are met, maximizing revenue and maximizing welfare become equivalent even. And this is in contrast to the utility maximization case, where there is a tension between maximizing revenue and maximizing welfare. And you know about the Myerson optimal auction and things like that. So in particular, in this case, for value maximizers, if we didn't have like gaming into account and like there was no basically auction or like pricing involved. The optimal thing to do would have been to sort the ads or the items based on in a decreasing order of their target adjusted value, this term here. And like in reality, the thing is that we don't know this exact target adjusted value, and the advertiser actually declares their value and their target for us to like use. So we need an auction still, but there is a big difference maybe in optimizing this auction. The first thing that we observe in this recent paper, upcoming paper in WWW, is that we can add quality boosts to such auctions and improve the quality of like the equilibrium after the bidder's response. So in particular, if we come up with a quality signal that is alpha correlated with basically the target adjusted value, then instead of maybe sorting based on their bids or bid times PCTR, we can add a term to the auction score, C times this quality score. And then the payment would be similar to like a VCG or like a GSP type auction. And under this change, if the quality metric is really correlated with the target adjusted value, the value of the equilibrium improves from the 1/2 approximation where we have C equal to 0. So this observation is useful in basically running this type of auctions if you can find quality signals that are like useful for advertisers as well. So the paper also, this first theorem is like in a simple setting that we don't have budget constraint, for example. If we add budget constraint and also think about like a general benchmark ranking, we can generalize this result with a different type of boosting, quality boosting technique that would basically boost. So you take into account the benchmark ranking. For example, it could be a ranking that comes from the liquid welfare maximizing ranking. And by boosting the higher ads in this ranking a bit more, we can show that we can improve the quality of the ranking and achieve an approximation to the welfare of the benchmark ranking. So this was like the theoretical results. In the paper, we also show on some semi-synthetic data that was inspired by some real data. We can show that basically by adding this type of boosts, either uniform boost or the benchmark boost that we discussed, we increase not only the welfare of the auction, which is basically a theorem, but also the revenue of the resulting auction. So the numbers that we get here are like for some semi-synthetic data, but it shows the trend and it shows the promise. So that's about improving the quality of the outcome. Next, if you want to understand the landscape of auto bidding auctions, we have to understand the information structure in this type of auctions. So advertisers in this type of auctions have two main private values that they have to declare. One is the value itself, one is the target. So in general, in economics, the value should be the private object, like, and basically the bidders have their own private value and they can game for that. But in this setting, the values in some settings are basically the clicks and conversions. And these are things that the platform can compute on behalf of advertiser, maybe even in some cases, like with the knowledge that the platform has, maybe better than the advertiser. So in this type of situations, and also like even if there is no like certain like machine learning system, the buyers in general in this type of environment may have less incentive to strategize for their values, because it's their conversion like through rate, for example, if it's their click-through rate. So if they game it, they can also, it has impact in other parts of their business. So as a whole, it makes sense to have like different type of information structure. We can assume basically we have both value and target as being private. we can assume that value is public actually and target is private, and the other way around, private value and public target. So we look at the optimal auction in these different environments. The first thing you observe is that for value maximizers, under the information structure, that values are public and targets are private, and the setting that the other way around, targets are public and values are private, the first base revenue is achievable by applying either a first price auction on target adjusted value or a second price auction with the payment scaling on target adjusted value. On the other hand, when both value and target are private, we can show that first base revenue is not possible to achieve, is not achievable, and characterizing the optimal auction in this case remains open. Just to make sure that we know what we mean by first base revenue, this means that we can achieve the maximum welfare and the revenue that matches this welfare. So it is possible to achieve first best revenue in these settings if we assume we have value maximizers. So an interesting observation is that the big part of the display ad market moved to a first price auction. Not for this reason, but it's like maybe reinforcing the fact that in more auto bidding world, it may be like an plausible move. But yeah, the reason for this was different, and I can talk about that in a different context. For utility maximizers, on the other hand, the story is more complicated and not as clean. It's not possible to achieve first price revenue. We can characterize open optimal auction in this paper and basically extend the results from another paper by my colleagues here. And it remains open to solve the problem in the case that both values and targets are private. So that's about characterizing optimal auctions in this auto bidding world, and there is more research to be done in understanding this market. We also did some recent work on the interactions between bidding and pricing. So the question here is, what's the dynamic of a bidder who is trying to learn their bidding strategy and a pricing, like an auctioneer who is trying to price against these bidders who are optimizing. So what's the dynamic? What happens if they both optimize or they both also learn their best strategy? So this is again an academic exercise to understand the situation and the convergence of these type of models. In the case of buyers' learning strategy, it turns out that under budget and ROI constraint, there is a simple uniform type bidding strategy that basically comes up with a threshold and takes the value of the advertiser and scale it with that threshold to declare the bid. That is actually an optimal bidding strategy with low regret. But now under this type of strategy and like a set of strategies that have low regret and like more generalizes this, we can show that the seller's optimal pricing strategy follows like a good like bell-shaped structure. The revenue has like a bell-shaped structure, and that helps us in basically learning the optimal pricing strategy for the seller as well. And if they both follow this, we end up in a like a low regret result for the seller as well. So this is like a topic of this other recent paper with my colleagues at MIT that we'll post on arXiv soon. I guess I'm done with the first section of the talk about like interesting questions and problems in this bidding automation board. There are many open questions. So I talked about how to improve the quality of improve the efficiency of the outcome, how to characterize the optimal auctions. And there are many open questions. For example, understanding the outcomes of basically non-truthful auctions like GSP is not completely understood, and also characterizing optimal auction when both target and value are private. So before moving on to this next section, I'm wondering if you want to take one question, Santiago.
Yes, thank you, Vahab. I think there's one clarifying question and then more like one high-level question. So here we have John Turner is asking about this informational assumption. And what he's asking is, would it be correct to say that although values for different auctions that an advertiser participate would differ, and therefore private, but the ROI target, the tau, is likely stable over multiple auctions and therefore learnable and known. So essentially, he's asking whether like private values change from auction to an auction, as opposed to the target being like the same for across many auctions.
So I guess in the target TCPA model, public value and private target is reasonable. This setting that like what you say makes sense. Actually, one thing I should have emphasized is that gaming the target itself is harder. So one reason that these markets are like more useful is basically in order to change or change your target value, you have to go through a more sophisticated gaming strategy that maybe I don't want to discuss like in details here. For that reason, making that assumption is also makes sense. And basically what you say makes sense in the target ROAS model as well.
So another question. Thank you, Vahab. Another question is more open-ended. That asks, what do you envision the future of automated bidding to be? Where do you think these markets are going?
That's a very good question and a hard question to answer. Like it's hard. So I'm following this market like in general a little bit, so I'm not like the best informed first of all, but it seems that the two types of bidding strategies that I highlighted are actually increasing in size for different reasons. This is the type of marketing that maybe the marketing department from like advertising companies are more comfortable with. They can also from basically advertising platforms, they can optimize very well under these constraints for advertisers. So I do think that at least in the near future, by that I mean in a couple of years, the number, basically the market will adopt these type of market bidding strategies that I highlighted more and more. And that's what I hear from people who are working in this area as well. But I'm not very well informed, and the market has its own surprises over time. There is also a chance that like with these new systems, like new things will show up, and like new gaming strategies will show up, and like new outcomes will come up like in the future. But in the near future, I think this will increase. Hope that answers your question.
Thank you, Vahab.
So maybe like in the interest of time, let me move to other parts of the talk, which is more about robustness. So like in order to be auctions that are, so the first part of the robust give you a sense of what type of problems we are talking about here. Let me give you this example of online ad allocation or budgeted allocation. It's known as the AdWords problem in the academic literature. So we have a bipartite matching problem where one side is advertisers, the other side is impressions. These are page views that people go, and when a page view arrives, we have to show an ad. So we have to decide which ad to show. Maybe we do greedily, we assign the best ad to basically the user at the time. So with this greedy algorithm, we get a matching. But then because we have budget constraint that goes across all ads and we have to optimize in real time, the solution that come out of the greedy algorithm may be suboptimal. So for example, in this just example bipartite graph that I showed here, the optimum solution happened to be 11, but the greedy algorithm gives the solution of value 8. So this defines like a performance ratio for an online algorithm that we adopt. In this case, it's 8/11. And this value depends on the instance and the arrival order of the page views or the online nodes. So this is like one toy, but very illustrative online optimization problem that we have to solve in an advertising environment. In the context of display ads, it's not budgets, it's the capacity. We have to show a number of ads from Toyota, from different advertising companies, and the ads, the users again arrive in some order. So again, there is a question of how to allocate in the online weighted matching setting. In these general online optimization problems, there are two schools of thought or two ways to analyze your algorithms. There is a worst case or adversarial basically model, and there is a stochastic and average case model. So in the worst case adversarial model, we don't have any assumption on the arrival of the page views, and we want to design an algorithm that optimizes basically the revenue or the objective on that algorithm over the optimum. And if we apply a greedy algorithm, we get a 1/2 approximation. The best we can do is like 1 - 1/e. On the other hand, in the stochastic case, we make an assumption on like the type of like arrival order of online nodes, and our goal is to optimize on average an expected value of the algorithm that we employ over the expected value of the revenue that the opt has. In this case, if, for example, it's like a fully stochastic model, it's possible to design algorithms that are asymptotically optimal if we can achieve 1 - epsilon competitive ratio. So the question that we are trying to solve here is which of these models should we stick with? Maybe it's worst case or adversarial model is too pessimistic, stochastic model is too optimistic. Maybe we have traffic spikes that, so basically a stochastic model is reasonable because we have some forecasting, we can forecast what's happening, but we cannot rely only on that. So we have to have robust models that work maybe with some stochastic, under some stochastic assumption, but they can do still well if we have traffic spikes and deviate from the assumptions of the stochastic model. So we have like proposed different models to analyze algorithms. The first was what we call simultaneous, adversarial, and stochastic model. So here we say both of these models are maybe optimistic or pessimistic. So let's come up with one algorithm that achieves good approximation ratio in both models. So now instead of defining one approximation factor, we define 2 approximation factors for each algorithm. And the question is, can we achieve and can we design an algorithm that achieves the best of both worlds, for example? And it turns out that in this paper, this old paper, we showed that when we face an unweighted online matching problem like this, where we just want to match users and websites, it's possible to achieve the best of both worlds. We can achieve 1 - 1/e, 1 - epsilon. But in the weighted case, when we have budgeted allocation, for example, it's not possible to achieve best of both worlds. There are some lower bounds that prevent us to get the best of both worlds, but we can like show algorithms that achieve some factor in the worst case, but some better factor in the average case. So that was basically an old paper, but still like the model for this simultaneous approximation is not satisfactory. The reason is that we don't have like this or that. Maybe we have maybe a hybrid model that we want to use forecasts, but don't trust them too much. Maybe like in practice also, we realize that the optimal online algorithms outperform simple greedy algorithms. When we make some stochastic assumption, we can beat basically the online algorithms, but they only work if the stochastic assumption is holding and our forecast is valid. But actually, like we realized that the hybrid type algorithms that basically constantly check for stochastic assumptions and like maybe correct for it achieves better bounds. So the question is, can we do good theoretical analysis of these type of algorithms? So the second model that we looked at in this context is, let's say we have some stochastic forecast, but we have some adversarial deviation from it. So in this model, we have maybe a stochastic model, but because of traffic spikes or adversarial corruptions, part of it is changed. And in this model, what we showed was, if we allocate items according to forecast, but then check for this, if we know the forecast, for example, here, check for the accuracy of the forecast, and then up to the online algorithm if the forecast is too off. How do we check for that? We can basically keep track of this parameter lambda, which is the optimum of the forecast over optimum of what's really happening so far. If this number actually is deviating from like from 1 here, then we up to the online algorithm. So as a result of this parameter, we want to design an algorithm whose approximation factor is a function of the prediction accuracy. So we want to say that our algorithm performs better and better if we have a better and better forecast. So this is in the spirit of also this algorithm design with machine learning advice. Basically, this is like there have been some recent work in this framework, and this older paper actually fits in this framework as well. That we use some ML advice, which is the stochastic forecast, and as a function of how good the forecast is, which is captured by this parameter lambda, we have an approximation factor. The approximation factor is, for example, this red curve, and we know also like some hardness result that you cannot go better than this curve. So it gives us like a platform to design actually better and better algorithms for these robust allocation problems. And the reason I'm talking about it actually in this venue is that we have like a piece of very recent work that I'm very excited about that goes one level further. So in the previous work, we made an assumption that we have some forecast and we want to correct for it. But in the new paper, we want to design an algorithm that is independent of any forecast, but we want the algorithm to be robust against many different models. For example, we want to be robust against the same adversarial corruptions based on traffic spikes or malicious perturbations, but we want to also deal with ergodic input. We want to deal with seasonal and periodic, basically, problems like in the input, and also maybe the fully adversarial model. So there is a question of, what are there simple algorithms that don't rely on any forecast and can achieve the best of many worlds like this? And the answer is yes. In this recent work with Sean Liu and Santiago Balcero, we have a framework of like basically dual-based mirror descent type algorithms that are very fast, very general. They can actually handle different type of objectives, even non-convex objectives. And more interestingly, they can provably satisfy good theoretical properties for a class of different type of models, for the stochastic model, in the adversarial model, fully adversarial model, adversarial corruption model, and ergodic and periodic models. And the interesting thing is that the algorithm does not use any forecast. It's like a simple dual-based algorithm that updates the dual after each allocation, and basically it achieves the best of many worlds. So by that, I'm done with the second part of the robustness, where we summarized a number of models in online allocation and showed how to apply basically online algorithms that achieve better and better performance against like different type of arrival models. I should emphasize that this is a real important issue in solving many of these problems in practice. We have, so like I have worked on like solving these online allocation problems in practice, especially for display ads. And the question of designing robust algorithms is very important. Like you really need to have an algorithm that maybe whatever forecast you have to have like a backup plan that if it doesn't work, we should have a good solution for it. And like the algorithms that we use in practice are actually closer to the algorithms that work well in the adversarial models that don't rely on any specific forecast. We inject like forecast here and there in a minimal way. So we try to remain very robust against like traffic spikes and things like that. Another thing I want to emphasize here before moving to the next section is we can generalize this conceptual idea of designing online optimization algorithms that are robust against corruptions to also online learning. And in that case, we want to design bandit algorithms that are that perform well under basically stochastic bandits, but with adversarial corruptions. So in these like two recent papers with Renato Pasleme and Todoris Likoris, we have like models of like bandit algorithms that work very well under stochastic assumption, but as we have an adversary and like a number of adversarial corruptions, the regret degrades gracefully as the power of adversary increases. So that's also interesting in the context of online learning. Now I'm going to the third part of the talk, which is about robustness against gaming and strategic behavior, or what I call incentive-aware learning. Do we want to take any other question, or should I move on? I guess if Santiago doesn't stop me, I'm going to continue. And we can take questions at the end.
Santiago, you're muted.
Sorry, yes. So yeah, I was saying exactly what Vahab was saying, that let's move on in the interest of time and we can answer questions at the end.
So in this third part, we want to discuss robustness against gaming and strategic behavior. And this is a line of work that concerns with how to learn, for example, prices, or how to design auctions that can learn from historical data, but also don't create incentives for buyers to change their like strategy or bid. And also, like at the end, we try to give some tools to buyers to check for incentive compatibility as a notion. Like a simple problem to communicate the gist of the main idea would be the problem of learning prices or reserves in a second price auction bid reserve. That's what we call SPWR, second price auction bid reserve. So imagine a seller who is basically running a second price auction bid reserve against a number of buyers. And if the seller is using historical bids or the empirical distribution of the bids from buyers to determine a reserve price, buyers would observe that and basically would, if like their own data is used, for example, in determining the threshold, they have incentive to declare like lower bids or like change their bids in a way that the second price auction with reserve computes lower reserves, because the lower reserves may benefit them in the future. So the auctioneer should find ways to either find like pricing knobs not using the information, or like basically learn from data in a way that's very robust against this type of behavior. So there are formal models for this. We can say each agent has a piece of information, each agent may report it, and the learning algorithm maps this to an outcome, and both agent and the system has like an objective they want to optimize. They have a utility and like a preferred outcome. So in this paper we call incentive-aware learning in large markets, we argue that if the each bidder is a small part of the market, and each mechanism or each mechanism from which the auctioneer is choosing from is what we call strongly incentive compatible, then there exists an approximately incentive compatible auction that the auctioneer can choose among these strongly incentive compatible choices, and basically satisfy approximate incentive compatibility. So let me explain the core idea in the next slide. The idea is to estimate, to use basically this softmax idea from differential privacy. So the idea is, instead of picking the outcome that has maximum revenue, for example, if you have the different type of reserve with different with these like X1 to XD revenues, instead of choosing the outcome that maximizes revenue or maximizes the objective, we choose the outcome proportional to the e to the power of lambda times the objective for that outcome. So we move from pure max to soft max, and on the way we achieve some differential privacy property that we are learning in a more private manner from the data, and at the same time we achieve basically what we call approximate incentive compatibility. So this is like a core idea. In like a more recent paper in NeurIPS 2020, we show actually, for the purpose of achieving approximate incentive compatibility, we can go beyond differential privacy. And like we don't need actually differential privacy to achieve the incentive compatibility. For example, instead of exponential function, if you use polynomial functions, we get better revenue trade-offs. So we observe that. And also we observe that basically using different type of soft functions can actually help us get better approximation guarantees in settings that the relation or the dependence on the dimensionality is like going to give us like much less utility. So this part is very technical, and the second result is actually very theoretical and not very, like practical. But the first one is actually useful in practice as well. With that, I want to also tell you about how to do reserve pricing. So here we are talking about reserve pricing or pricing in a static auction. How to use your data, like one's data, to learn something in a more robust and privacy like preserving way. But now I want to tell you about how to learn prices in like a more dynamic environment. And for this, we turn to contextual auctions because our results work in this setting only. So in this setting, the values for buyers come from some distribution that has this type of form. It has a noise that is known to the auctioneer, and another value part, which is the dot product of the preference of the buyer and basically a vector of context. The context, this vector of context, that's the contextual information of the, for example, the web pages, that's known to the auctioneer. The part that's not known is these preferences, and these basically these vectors are not known. So in an environment like this, we show how to set like a pricing scheme that we call a dynamic incentive-aware learning pricing scheme that basically achieves a sublinear regret against the optimal second price auction with reserve in hindsight. So the insights from the algorithm that we use to achieve this sublinear regret is that we first of all use episodic learning to address incentive issues. And also, more importantly, we we don't use the whole historical data. We use like a censored version of the data and not, for example, the bids, but only the fact that the bidder is served or not under some reserves that we set in the past. So this type of censored data can help us learn in a more robust way. So now I'm going to switch to, so that's like also an area that can be explored much more and very interesting and very important area. I guess now I want to tell you about helping advertisers or buyers understand incentive compatibility measures. So here the goal, so we know that the market has adopted, like in the advertising market, there are first price auction, there are generalized second price auction. It's not that they're like advertising platforms are running truthful auctions. The question is, how can we help buyers to measure how basically non-truthful or like non-incentive compatible like an auction is? And like we want to design a system that's very simple and like data driven. We can easily compute by running some simple experiments or like looking at the data. So we introduced this notion of IC metric that we call basically ISIC. This is a metric that's inspired by the way that the Meyerson lemma is defined, if you are familiar with that. So instead of basically, so like if you know the Meyerson lemma, you see that we are basically taking expectation in some of the terms, but the idea is basically to see in expectation how much the user benefits by perturbing their, how much the buyer benefits by perturbing their bid with like a small factor. And this ratio gives us basically a measure. So the interesting thing about the measure is that for incentive compatible auction, like second price auction, the measure is 1. The first for pay your bid auction, the first price auction, the measure is 0. And more interestingly, if we randomize between basically a first price auction and then second price auction with like a probability lambda, the basically IC metric that we compute is actually 1 minus lambda. So it captures the trade-off of how incentive compatible your auction is in some sense. So we also find closed forms for like soft floors, for generalized second price auction. We do some of these observations in the paper. We also observe that the smaller this metric is, the larger the incentive buyers have to share their bids. So this is like related to the automation, like bidding strategies, and like we can show that systematically, the larger the value of this metric is, the larger incentive they have to basically shade their bids, which is like important part of the bidding strategy. We also define a dynamic version of this IC metric that's related to dynamic incentive-able learning, thing that I don't have time to cover here. But interestingly, on data also, we observe that, for example, in a generalized second price auction, the IC metric decreases as the number of slots for the generalized second price auction increases. We also observe dynamic incentive compatibility measure for different ways of computing reserve prices based on your data. So I encourage you to look at this paper that defines this incentive compatibility measure. And we hope that this can be used as a tool actually to design auctions that are good in terms of incentive compatibility measures. This area also has many important open questions. For example, the topic of incentive-able learning in high dimensional space, or the question of giving the buyers more data-driven tools to find their optimal bidding strategy, or actually the question of finding ways to learn these reserve prices in heterogeneous markets by looking at other parts of, so this idea of using other bidders' bids to find like a good auction or a good price against like the other auction like buyers is very interesting if you can do practically and like effectively well on real data. So this is the third part. The last part was meant to be skipped actually, but now I have 5 minutes, so I'm going to give you the core idea. This is the most technical part of the presentation. It's about robustness in dynamic mechanism design. Now, in the second part, we talked about online allocation. The third part, we talked about incentives. So now this fourth part combines the two, and we are talking about online repeated auctions. So we are running online and also repeated auctions in a stateful manner, the way that dynamic mechanism design works. So this area needs a lot of attention from robustness point of view, because most of the dynamic mechanisms that are out there rely too much on predicting the present, having good distribution, like Bayesian assumptions, and also like a specific buyer behavior. So in a sequence of papers, we try to move more and more toward what we call robust dynamic mechanism design. And given that I have some time, I'm going to give you the core idea behind at least the first couple of papers. So the model here is a repeated auction. The buyer will draw from like a distribution in each round, and the incentive for the buyer is to maximize his current payoff in each round, but plus the expected value of the payoffs it gets in the rest of the horizon. So we are given this horizon. So in the dynamic auction setting, we are trying to link decisions over time and design auctions that basically can get better efficiency or better revenue by looking beyond one single auction. But just doing that may make us actually rely too much on forecasting the future, or forecasting or relying too much on these value distributions for the future rounds. So in like this recent paper, the econometrica paper, we introduced this notion of non-clairvoyant dynamic mechanisms. We say, what if we design an auction that does not rely at all on the future forecast? So like we want to design an auction that only relies on the forecast of the current stage and is independent of all the like future stages. It turns out that even with this type of restriction, we can still achieve like a constant factor of the optimum dynamic mechanism design that's much more than the optimum static mechanism. So we use the idea of bank account mechanisms and randomizing over strategies. We also show lower bounds here. So this was like paper that we wrote a couple of years ago, and like it appeared last year as a journal version. But what it doesn't do is it still relies on the good forecasting of the current like stage. So it relies on perfect distribution of knowledge of the present. It doesn't rely on the future, but it does assume that you have perfect distribution of knowledge of the present. And in this like recent papers with Yuan Deng and Sebastian Lai, we show actually how to use noisy estimates of this distribution and or future distributions in designing non-clairvoyant and clairvoyant optimal basically auctions with low regret in this environment. So the results are technical, but this is the first type of work that combines basically in the contextual setting what we call dynamic incentive-aware learning, what we had in the second part, and dynamic mechanism design in its full generality to the best of my knowledge. So this is like one level further for robust dynamic mechanism design. We also reported some empirical results in a paper where we basically design like a simple set of mechanisms that under some like noisy estimates can do better than much better than the static mechanisms. I guess I'll skip this last part, which is about robustness against buyer heterogeneity. I guess the topic is, I'm going to be here and tell you that dynamic mechanism design also relies on the utility function that we assume on buyers. but the buyers can be myopic, they can have full locate, they can have limited locate, they can run a no regret policy, they can run policy regret, but they can have different type of strategies. The question is to design one auction that does well against different types of buyers. So this is the first paper, like if you have a single buyer, but you don't know the type, how do you run a robust auction against that type of buyer? And the second one is about how to run an auction that works well against a mixture of different types of buyers. So I guess the research agenda here is to move toward more prior-free dynamic mechanism design, mechanisms that don't rely on predictions or like can deal with noisy predictions and so on and so forth. 1 minute over time, and I'm done with the fourth part as well.
Thank you so much, Vahab. Yes, 1 minute over time. I think you did great with the timing. Let's stay a few more minutes to answer some questions. So you talk about like kind of machine learning advice in online algorithms. So can you expand about that? Like what does machine learning with all this predicting power that has exploded in the last few years can provide to kind of online algorithms and online allocation problems too?
Good. I'm happy you asked this question. So there is a very close relation between. So if I understand the question is like one aspect of the question is what is the relation between the algorithm design with online with ML advice and these online robust optimization literature, or can we use insights from that to help here? The answer to that question, if I understand correctly, is that I find actually these like robust online optimization results an important case in the ML advice, where the ML advice is actually the forecast. So like in the context of ML advice, we can also assume other types of advice that may not be like distribution forecast, maybe like knowing some parameter somehow that that will help us very well in like designing achieving a much better approximation factor. But I guess the most important question that I know in that category of problems is this type of problems, that you want to design a class of algorithms that can benefit from machine learning advice. Like by that, I mean basically some forecasting that you can get out of some machine learning system. But then they are not so that would be a stochastic optimization, but making sure that you don't rely on that type of advice too much is what we call the robust optimization here. I hope that I answered that question to some extent. But like maybe I can also say that there may be some machine learning models that shed light on like what type of machine learning system can provide what type of advice that helps like the online algorithm in a more effective way. For example, knowing that doing like learning some type of like parameters is easier should be a guideline of like designing stochastic algorithms based on that guideline, because that's something that we can learn more in a more robust way. I don't know actually if I answered your question, but
no, it's okay. It's okay, thank you. So
then
relation
between these topics.
So to conclude, so I think that it's great that you mentioned this like kind of open problems, but if you're talking now to a young researcher who is just starting, and is looking like kind of for attractive problems, what would you single out as one of the most interesting problems that are out there from your perspective?
So if you want to do some things that are like more relevant to industry, industrial problems, I think what I presented here, the first one is very closely related to online advertising industry, and I would insights about what are the best bidding algorithms, what are the interactions between bidding algorithms and different type of auctions. That will be received well in industry, in this part of the industry. The online learning and online optimization part with adversarial corruption is also very well received, both in industry, in machine learning theory community, and also even more in academia. Like these are very hot topics. Incentive-aware learning, the same. I think the topic is relevant, maybe not as broad as the first two topics, and the very last one is like more niche for like auction design. But there are like many interesting questions in this space as well. So like I guess from the sequence of the problems I mentioned, there are like more and more. At the beginning, it was more industry oriented, and like it became more and more academic. But they're all very interesting. Santiago?
Yes, sorry, my internet is choppy. Sorry.
All right, maybe we could thank the speaker and close the webinar now.
Yes, thank you, Rene. Well, let me thank. I think that we have connection problems, so let me thank Vahab for his seminar, and then if you have any other questions, please feel free to send them via email, and we'll be happy to get back to you. Thank you.